Hello, Year 12. Right, that's you, that is. I've just written Year 12 on there, so you know it's you. This is the homework that I've just sent on Satchel 1. It's gas reaction questions, but this time looking at them in exam papers. Now, they're hard. There's no two ways about it. They are hard, but what we're going to do is we're going to practice that approach of I know these questions are going to look hard, but underneath it all must be an easy solution. All right. So you're not there yet. You're only little. You're only young. You're only just started your A-level journey, but you'll get there. So it's about being able to see past all of this distraction and find out what the easy answer is. Saying that, I'm going to actually ignore the multi-choice questions first because they're really quite tricky, and I'm going to start on question 5. So just like you, I've printed this off at home. Probably just like you, I've got little errors with the printing where it's printing all sort of 2 pages. But, so I just want to show you, this is me working at home now. School's finished. And, bit of solidarity and all that, trying to sort of do what you're having to do. So, question 5. Sorry you got the shadow again, but, you'll grow to love it, I'm sure. Oh, hang on. What's this new tattoo I've got on my hand? Units. PVNRT, watch out for units. Right, a sample of pure MgNO3 magnesium nitrate, NO3 twice, MgNO3 twice, was decomposed by heating. That's known as thermal decomposition. Thermal decomposition, as shown in the equation below. Just a little aside here, you can tell when something is decomposed because you start with one thing and it ends up with more than one thing. So that one thing has been broken down or decomposed, rather than having another reactant like oxygen. Anyway, so this is how I would approach this. A 3.74 times 10 to the minus 2 gram sample of this was completely decomposed by heating. So what have they given me? I'm going to write this 3.74 times 10 to the minus 2. I've written it directly below here. This is the way that I lay out my calculations. Was completely decomposed by heating. Calculate the total volume in centimeters cubed of gas produced. Okay. All of that's gas. All of that is gas. All right. I remember this question. 5 moles of gas are produced there. Now, you wouldn't have thought that, would you? You might have gone. You can work this out by working out moles of NO2 and moles of O2. But actually, I'm just going to work it out. 5 moles of gas are produced. You'll come on to this a little bit later, but a mole of oxygen gas takes up the same amount of space as a mole of nitrogen NO2 gas. So all gases occupy the same volume under the same temperature and pressure. Anyway, I'm realising that 2 moles of this are going to make 5 moles of gas. I've got a grams. What else have they given me? PVNRT. Let's collect terms. I'll collect them over here. PVNRT. They're giving me a pressure, 100 kilopascals. Units, 100,000 pascals. 60 degrees C, so I need a plus 273. That's 333 Kelvin, so I've done that. R is 8.31. N I haven't got, and they want V. Alright. So, it's one of those like we were practicing the other day, but it's just got this added difficulty of having 4 NO2s and an O2. So first thing to do, I've got grams of this. So if I take grams and I divide it by the MR, the MR there, magnesium, 2 nitrogens, 148, and it's a 0.3 for the magnesium, 148.3. So if I divide those by that, you will get, what will you get here? So if you haven't done this question yet, pause the video now because I've given you a little starter. Now you've got a little plan. What I'm going to do is I'm going to go down to here, work out the moles of magnesium nitrate, because we always turn grams into moles. That was my other tattoo last week, or the other day. Then I've got 2 moles of this will produce 5 moles of gas. So that'll tell you that you've got this many moles of gas. That's your N. Plug that in here and you'll get a volume. I'm pretty sure that will just work. To the point that I'm not going to do that answer. 148.3, that'll give you a moles of there, which will be worth 1 mark. Then you'll do this 2 to 5 ratio, which will get you another mark. You could have done a 2 to 4 ratio first and then a 2 to 1 ratio separately and added them together, but that's a bit of a faff. So you put that in there, then this will be worth a mark. You'll get a volume. Now here's the final thing. Your volume is going to be in meters cubed, isn't it? So you've got a little cheeky conversion there at the end as well. So this is not me showing you how to get the exact right answer, but that is the process, and you've got the mark scheme in the back. What I'm trying to show you is I didn't approach this and go, oh my goodness, this is going to be hard. I've gone, oh right, I've done grams into moles, I've used a ratio, and I've plugged it into PV/nRT, watching out for units. Drop my pen. Gonna have to go under the table. Running commentary there. Right. Let's have a look at the next question then. What else have I given you to do? Potassium nitrate, KNO3. You know what? I had a year 13 today who said potassium ions were K-. I know, you're allowed to laugh at home. You're allowed to do a geeky little laugh. Imagine that. A year 13 student said potassium was K-. Madness. KNO3-. So there you go, that's where it comes from. Potassium nitrate decomposes on strong heating, forming oxygen, O2, and a solid Y as the only products. A 1 gram sample of KNO3, MR 101.1, was heated strongly until it fully decomposed into Y. Alright, so it looks like we've got this turning into this and this. That's what I'm getting so far. I don't know where this is going, and I'm getting a little bit nervous, but it'll be alright. A 1 gram sample of KNO3 gives me the MR was heated strongly, number of moles, so that's 1 divided by 101.1. That is an absolute doddle. Right, so there are easy marks. Checking the mark scheme actually rather than plug it in. 9.89 times 10 to the minus 3. Well, that's such an easy mark, isn't it? Alright, so a bit annoying. I've got to now go over 2 pages. Let me go into push that bit into the shadow. But I'm already seeing PV/nRT, so I'm now thinking units. Bear with me. It's a professional operation here. Is this where I say like and subscribe? Like and subscribe? Don't do that. But you can if you want. Makes me feel happy, doesn't it? People are watching it. At 298 Kelvin and 100 kilopascals, so I'm already thinking PV/nRT. The oxygen gas produced in this decomposition occupied a volume of, so I've got a T, a P, and a V. Right. Ideal gas equation, PV equals nRT. God, they're giving you some easy marks on this paper. State the ideal gas equation and use it to calculate the number of moles of oxygen produced. So they're even telling you to do that. Right, so N equals, divide both sides by RT, PV divided by RT. Collect me terms. PV/nRT. Physicists, you practice this sort of thing all the time, don't you? Collecting terms. 100 kilopascals, you're not catching me out there because my tattoo says units. Volume equals 1.22 times 10 to the minus 4. Are you happy with these units, everybody? Because I am. They're in meters cubed. That's nice of them. N equals unknown. That's what we're being asked to do. R equals 8.31 joules per Kelvin per mole. And temperature equals, better to give it, oh no, to give it 298. Well, that was fairly straightforward, wasn't it? Stick all them in that equation. P times V divided by R times 2. Bibbidi bobbidi boo. What you get, put it together, and what have you got? Bibbidi bobbidi boo. 4.93 times 10 to the minus 3. Sorry I didn't plug that into the calculator. I just looked at the mark scheme again. You've got to lay it out. But what I'm showing, I'm only looking at the mark scheme on the last bit. I'm just seeing if these are a bit tricky. That question's a doddle. Question 7. Right, again. Staying calm. I have not practiced these questions, so I am at risk of looking like a fool, like I nearly did in the last video. But I am confident that this will be alright. Alright, I remember this question. Not because I've done it, but because I just prepared it for you. Under suitable conditions, magnesium will react with dilute nitric acid according to the following equation. Look, dilute, aqueous. It will make magnesium nitrate. Magnesium plus nitric acid makes magnesium nitrate plus hydrogen. As you know from your GCSE, metal plus acid makes salt plus hydrogen. Right, so then you've got this information here, centimetres cubed and moles per decimetre cubed. That is why part A of this question is missing, because it was about reacting volumes, which isn't difficult, we just haven't done it yet. So that's why I said in a second experiment. The first experiment was part A. So let's have a little look then. In a second experiment, this many moles of hydrogen gas, that tells you how many moles, so that's useful, I don't have to work that out, was produced when another sample of magnesium reacted with dilute nitric acid. Calculate the volume that this gas would occupy at... Okay, I'm going to write the equation out again, because I've got a bit of a gap here. 2HNO3 makes MgNO3 twice, plus H2. What did it tell me? 0.512 moles of gas. So they're already telling me the moles of this. So that's 0.512 moles of hydrogen gas. I've used that data. I like to do this, tick off the information when I've used it. It was produced when another sample of magnesium reacted with dilute nitric acid. Calculate the volume that this gas would occupy. Oh, well, I've overthought this question, haven't I? They just want me to work out the V here. I don't need to do any of this. It's okay. P, V, N, R, T. See what I've got? T, 298. R, 8.31. N, 0.512. Don't need to do anything with that because it's already in moles, isn't it? It's already moles. A lot of you might have tried to do something with that. V, they want me to calculate. P, 96 kilopascals. 96. 0, 0, 0. Well, that's an easy question too, isn't it? I hope you found it easy, or you might be getting from these videos. You might be bored senseless, but you might be getting from these videos that underneath it all is a very easy answer. So what have I got to do? I've got to work out V. So if PV equals nRT, I've got to work out V. V equals nRT divided by P. I'm going to look at the mark scheme now. N times R times T. Here it is. N times R times P divided by V. All your numbers correct. And then include units in your final answer. So it'll be in meters cubed. Or you could convert it to centimeters cubed if you're weird and you wanted to do that. I don't know why you'd want to do that. So anyway, there's your 3 marks. 1 for plugging the numbers into that. 1 for quoting this, and 1 for getting the right answer with the right units. Right then, question 7C. Hello, empirical formula. Wow. Well, we've done some of these. So this isn't PVNRT, so this is empirical formula. Is my brain in the mood for empirical formula? Well, it hasn't got a choice. I've got to do it. It's 9 o'clock, but I've still got to do it. Concentrated nitric acid reacts with magnesium to form an oxide of nitrogen, which contains 30.4% by mass of nitrogen. Oxide of nitrogen, it basically means it might be NO, it might be NO2, it might be NO3, it might be N2O4. It's that's all it means, an oxide of nitrogen. Do you know what all the oxides of nitrogen are? I mean, I do, but do you? All right. Some of these, if anybody like real chemists are watching this, some of these may or may not be true oxides of nitrogen. Right, it contains 30.4% by mass of nitrogen. Calculate the empirical formula. Empirical formula questions always do this. Elements at the top. Well, I know nitrogen's in it, and that's 30.4%. What's the other elements? You're not given any other information. The other information is it's an oxide of nitrogen. So it's just made of nitrogen and oxygen. What's the percentage of this? Well, let's do some maths. 69.6. I'm not going to tell you how I did that. You can work that out. It's not in the question, but I've worked it out. I reckon that's probably worth a mark. It is, it's worth a mark for that. What a gift. Okay, then you drop down the arrows here. You divide this by the AR of that, which is 14. This by the AR of this. Notice I say AR there because I'm dealing with atoms. It's all about being precise. Alright, A-level chemistry, it's all about being precise. I'm going to do this one rather than look at the mark scheme. So, what you do when you're doing an empirical formula, firstly, you divide by the ARs and you get what I like to call a raw ratio, or a crude ratio, or a rough ratio, which never is the answer. 69.6 divided by 16 and this gives me this one, 4.35. But it's a ratio nonetheless. It tells me I've got 2.17 of these, the 4.35 of these. Which is not a very useful ratio because we're trying to get the simplest whole number ratio. So the next step is to divide both these sides by the smallest number. So I'm going to divide that by 2.17 and this by 2.17. So that's going to be 1, obviously. And this number is still sitting on my calculator, so I'm going to divide that. Oops, I've divided it twice. Divide by 2.17. 2, 1 to 2. There's 1 nitrogen to every 2 oxygens. NO2. Whew. Does it ask for a formula? Calculate the formula. Yeah. Don't just stop at the ratio. Don't stop at the ratio. Drop your pen and celebrate. Read the question. It wants the formula. Although you can do a pen drop after that. Yes. Okay, next. I'm enjoying this. I'm coming across as being quite good at chemistry. Right, question 9. The other set of questions I've set yet is a bit hard. And the multi-choice at the start of this are hard as well. Right, phosphoric 5 acid. You don't know what that means. It's an oxidation state. It's effectively like a charge on the phosphorus. We do that later on. I'll sort of let you into a bit of a secret about it though. All of the oxygens you consider to be -2. Oxidation state it's called. -2, -4, -6, -8 because there's 4 of them. The 3 hydrogens are all +1. So you've got like -8 from the oxygens, +1, +2, +3 from the hydrogens, which means the phosphorus must be 5. That's where this 5 comes from. You don't have to remember that, by the way. Just telling you. Phosphoric acid is an important chemical. It can be made by 2 methods. The first method is a 2-step process. In the first step of the first method, okay, to make phosphoric acid, phosphorus is burned in air at 500 degrees C units to produce gaseous phosphorus oxide. Okay, 220 grams of phosphorus were reacted with an excess of air. Give me grams. What's that other tattoo? Turn grams into moles. Anyway, let's do it. I'm going to write it out here again just because I want to. Phosphorus. 5 oxygens. 1 mole of phosphorus to 5 moles of oxygens makes 1 mole of P4O10. Gas. Calculate the volume in meters cubed of gaseous phosphorus oxide. Look what I do. I do that and I write a V. That's my target. Produced at a pressure of, right, PV nRT. I'm going to collect them over here this time. Pressure, 101,000. Done. Temperature, 500. You need to add 273. 773. You're so good at maths. 8.31. Right, it's one of them where I haven't got an N and I haven't got a V. But I have got... Susanna Door! That's my son back from Cubs. Just proving that I'm at home. Right, and do I edit that bit out? No, because it involves editing. I don't know how to do that. Right, but I need right, what have I got? Come on, I got distracted there. 220 grams of phosphorus. 220 grams. This is, again, it's an easy question. It really is. Right, what you're going to do, you're going to go 220 and you're going to divide by the MR of phosphorus, which is P4. This will give you the moles of phosphorus. You're then going to go across with a ratio arrow. Unless you're in Dr. Halliday's lessons and you don't like using ratio arrows, in which case you're going to say it's a 1-to-1 ratio and do it on a separate line, which is fine. This will give you the number of moles of P4O10. It's a 1-to-1 ratio. Let me just check because I did get distracted by a child. When you've got the moles of that, you can plug this in here. Then you can rearrange for V because you'll know that PV equals nRT. Oops, going off the screen. So you'll know that V equals nRT divided by P. This will give you a volume in meters cubed. That'll give you a volume in meters cubed. I don't see any problem with that because it asks for it in meters cubed, and then you'll have to give your answer to 3 sig figs. The 3 sig fig things is, whoa, focus. I'm gone a bit blurred. Oh, it's happy now. So, yeah, it looks fine. I'm just going to check the mark scheme, see if I've missed anything. If I have, I'm sorry, but I don't think I have. Question 8. A, B. Mark scheme. So the mark scheme's a little bit complicated. Right, what's it say? Correct conversion of temperature and pressure, so 773 and 101 times 10 to the 3, or 101,000. Number of moles of P is 220 grams divided by the MR, which is 4 times that, 1.77. 1-to-1 ratio, so it's 1.77 N times R times T divided by pressure. Yeah, it's fine. 3 sig figs. Alright, let's have a look at the next one. Percentage yield. Right, percentage yield calculations. Remember what I've always said about them. Percentage yield calculations are never just divide one number by the other. They are always pretty much some sort of reacting masses calculations first. Because remember, a percentage yield is effectively what you did make divided by what you what you could have made. So you need both of these values. You've got what did you get divided by what you could have got. So you've got to actually work out what you could have got first. So let's just take care here. I'm going to put the numbers next to the things on the equation, next to species on the equation. In the second method, 3.5 kilograms of calcium phosphate are added. So 3.5 kilograms units, that's 3,500 grams, are added to an excess of aqueous sulfuric acid, so don't worry about the sulfuric acid. 1.09 kilograms of phosphoric acid are produced. Now, I don't fall for this trap here. That is what I actually did get, but I need to work out what I could have got or what I should have got. So I'm just going to put this 1.09 up here for later. 1090 grams is what I got. I've got to now work out what I could have got by going down, across and up. So I'm going to work out the moles of Ca3PO4. That will require you to carefully work out the MR and divide it. You've then got to carefully do the ratio, which is 1 to 2. That will tell you the moles of this. So you're going to get a mark for this. You're going to get a mark for this number of moles. And then you will work out the mass of H3PO4 that you could have made, or in other words, that you should have made, the maximum mass amount possible. Only then will you divide 1090 by this value here. So I'm going to actually just get the numbers from the mark scheme. So again, if you haven't done these questions, you should really have attempted them. That one should have been fine. So what have we got here? So it says here, first step, 3,500 divided by 310.3. So that was 310.3. And that gives you this number of moles down here, which is, where are you? 11.28. You've then got a 1 to 2 ratio, which is 22.56 moles. Then you're going to times it to get up here by timesing by 98. That'll give you a maximum of 2211, but you only made 1090. Why didn't you make 2211? Well, you might have, it might be a reversible reaction, there might have been some lost in purification, and you've done those sort of questions with Dr. Halliday or with myself. So you do that, you times by 100, you got yourself a percentage yield. Let's scan for, quickly, just for sig figs. No. Sig figs, I would do in this case, I would give the answer and then I would record my answer to 3 sig figs because everything is to 3 sig figs. It's not always what you have to do, but it's good practice to get into it. Record the answer that your calculator spits out. So I would do 1090 divided by 2211 equals, and then I'd do times 100. So I'd write something like 49.299, and then I'd do 3 sig figs, 49.3, and in brackets I'll put 3 sig figs. Units, percent. Yeah, there you go. I'm nearly done, because this is a 24-minute video. This is the most I've ever worked. I've never worked this long in a lesson. I'm normally having a brew by now. Don't tell ahead. Don't drink in a lab. I'm normally having a brew outside of the lab because it's break time. That's what I meant to say. Right, explain whether the first method or the second method of production of phosphoric acid has a higher atom economy. You don't know because you're missing part B. So there you go. That's an easy one. But what you would have done, I imagine here, it's something to do with, in this second method, you're making a lot of waste, and the first method didn't produce any waste. So I imagine the first method is more atom economical. You know what? I think I've finished. Oh no, multi-choice. Yeah. Do you pause your video now and do this tomorrow? Maybe you do. Maybe I'll write this. Pause your video, absorb what I've done so far, but I'm going to crack on. I'm 25 minutes in and I've got to talk about these multi-choice. Now these multi-choice should take a minute, but they're a bit tricky. Now these are ones I might find too tricky, in which case, I will see anyway. Two sealed flasks are the same volume are left side by side. Alright, two sealed flasks with the same volume, that's important, same volume, same V, because they're gas reaction questions these. Flask A contains this many moles, that's an N. Flask B contains 340 milligrams, so that's 0.340 grams of a different gas. Both gases have the same temperature and pressure. Which gas could be in flask B? Whoa. Okay. Right. Volume of flask 1 equals volume of flask 2. That's what I've got so far. If you've got the same volume of gas in each one... if you've got the same volume of gas in each one, doesn't matter what volume of gas it is, and this is something that you'll do next time. It doesn't matter what volume of gas, what the gas is. 1 mole of one gas occupies the same amount of space as 1 mole of another gas. That's just a fact of gases. Because gases are so spaced out, it doesn't matter if you've got a hydrogen gas, which is tiny, or CH4, which is bigger. A mole of hydrogen and a mole of CH4 occupy the same space. So this is a bit of a trick question. If you've got the same volume of gas being left side by side, you've got this many moles of methane in one, that means you've got this many moles of a different gas in the other. That means you've got 4.0 times 10 to the minus 3 moles of this second gas. Now you're going to do a bit more on these sort of things later, but that's what it means. That's the key. You've got a moles now and you've got a mass. It's not PV equals nRT this. I've got this many moles and I've got a mass. Hang on, so it's mass divided by moles. If I do 0.340 divided by 4 times 10 to the minus 3. 0.340 divided by 4 times 10 to the minus 3. 4 times 10 to the minus 3. 85, so that's the MR. The MR equals 85. So one of these must have an MR of 85. 12, 13, 14 plus... that could be it. I'm going to... 35.5 plus 35.5, 71, 72, 73, 83, 84, 85, that one. Hey, just checking. Could you hear me sort of almost cheating? Oh, it's 8 here. Right, yeah, A, tick. Do you know how you know it's not a PVNRT? Because they didn't give you 8.31 is R. They will always give you R equals 8.31 if it's a PVNRT question. So it wasn't. There was clearly a trick. It was the fact that if they've got the same volume, that means they've got the same number of moles. That was the key bit of learning there. Right. Which of these samples of gas contains the largest number of molecules? The largest number of molecules is basically the biggest number of moles, because we know that 1 mole contains 6 times 10 to the 23 molecules. So this is often a little trick here where they're trying to use the word molecules instead of moles. Whichever one of these gives you the biggest value for N is going to be the answer. Right, let's see if there's an easy way of doing it. N equals, so what does N equal? N equals, so PV equals nRT. PV equals nRT, so N equals PV divided by RT. And what are they giving me? So they're giving me a pressure, a volume, and a temperature, and R. Which of these contains the largest number of moles? I could probably do it by comparison, or I could just plug all the numbers in. PV divided by RT. Alright, I'm going to do it by plugging all the numbers in. This is probably not the most efficient way. Because if you look in there, that's the biggest pressure. Highest temperature. Having a high temperature is bad. Having a big pressure is good. Yeah, somewhere in the middle, innit? And having a big volume is good. I don't know by looking at them. I'm going to plug the numbers in. PV divided by RT. So this is 1 times 10 to the 6. So these units are fine. So you just go pressure times volume divided by 8.1 times 10. You know what? I can't be bothered doing it. Honestly, I really can't. Can you work that one out yourselves? I think that one's alright. You just do P times V divided by R times T. And one of those answers is the biggest. Alright? Good. That just doesn't look hard. Right, it just looks boring. Anyway, 30 centimeters cubed of xenon are mixed with 20 centimeters cubed of fluorine. You don't know how to do this yet, so I'm going to leave that as a special treat. Alright, it's easier than it looks. But do you notice there, you're not given 8.31 or anything like that. So it's not PVNRT. It's a different way, and it relates to the fact that 1 mole of gas occupies the same volume as another mole of gas. Do I do this now? No. I'll wait to see Dr. Halliday's video and then you can have a go yourselves. Right, 130 centimeters cubed of oxygen and 40 centimeters cubed of nitrogen, each at 298 and 100 kilopascals, were placed into an evacuated flask of volume 0.5 decimeters cubed. What is the pressure of the gas mixture in the flask at 298? (130 centimeters cubed of oxygen and 40 centimeters cubed of nitrogen, each at 298 and 110 kilopascals, were placed into an evacuated flask of volume 0.5 decimeters cubed. Okay. Right. It's one of them, and it's because it's the last one. Right. Well, what have I got? I've got a temperature equals 298. I've got a pressure VNRT. I've got I've gone a bit quiet now, haven't I? I'm thinking this isn't that straightforward. Pressure equals 100 kilopascals. N and a V. 130 centimeters cubed of oxygen and 40 centimeters cubed of nitrogen, each at 298 Kelvin and 100 kilopascals, were placed into an evacuated flask of volume 0.5 decimeters cubed. What is the pressure of the gas mixture in the flask? I think I've got to do a couple of little... There must be a way of doing this better. It doesn't matter that they're oxygen and nitrogen, does it? It doesn't matter that they are oxygen and nitrogen, because each gas occupies the same space, occupies the same volume. So I've got these small volumes of gas, and then they've been put into another flask and they've filled that space. Right, okay, so I need to do a before and after situation. Right, before they were put into this new flask, I had 170 centimeters cubed, 170 centimeters cubed of gas, and that was at 100 kilopascals, 100,000 pascals. nRT, and then I've got 8.31 and I've got temperature of 298. So I can work out how many moles of gas I had, moles of oxygen and nitrogen I had. Alright, I think I'm onto this now. Right, so if PV equals nRT, number of moles equals PV divided by RT. So I'm going to do pressure 100, this is pressure and they're trying to get this right, 100,000 times 170 centimeters cubed. Now that is, you need to do times 10 to the minus 6 to get that into meters cubed, because it's all about units. Times 170 times 10 to the minus 6. all divided by 8.31 times 298. Okay, let's see if I can do my calculator. 100,000 times brackets 170 times 10 to the minus 6 close brackets equals 17 divided by 8.31 times 298 close brackets equals 6.84 times 10 to the minus 3. So the number of moles of oxygen and nitrogen that I had was 6.865 times 10 to the minus 3. I'm then going to put all of those moles of gas into this second flask, which is a different volume, which is... So I'm now going to put these moles into a second flask, which has got a different volume of 0.5 decimeters cubed, which is 0.5 times 10 to the minus 3 meters cubed. And they wanted me to work out the pressure. Cool. So I've got a second equation to do. PV equals nRT. I need to work out the pressure. Pressure equals nRT divided by V. Alright, I've got my N still sitting on there. So I'm going to times by R times 8.31 equals, then I'm going to times by T times 298 equals 17. Oh, that number's popped up again. There's a trick here that I've missed. Okay, then I'm going to divide that by 0.5 times 10 to the minus 3. 34 kilopascals. Oh, right. I've done enough on this video. I've missed the trick there. I've missed something. What have I missed? Oh, you know what? I didn't need to do that. I think it's right. You can have a go at this. You can pause the video now and go home or whatever you're already home. You've got these two gases. You're going to mix them together in a flask. I think there's a trick here where you can say the number of moles in the first situation when they were unmixed equals the same as the number of moles in the second situation. And then you can therefore say that if N before equals N after, PV equals nRT. That means that the PV divided by the RT before, the PV divided by the RT before equals the PV divided by the RT after. Yeah, and then you can basically cancel out the R divided by T because they're the same. Same R, same T in both situations. And then you've got the pressure before times the volume before equals the pressure before times the pressure after times the volume after. And there's your shortcut. You can rearrange that. And I didn't see it because I sort of panicked. And actually I saw a way that was slower, but it would get me the answer. I hope you might have to rewind that again and see my brain working very hard. I felt straight away when I was doing this, the fact that I was having to do two calculations did not feel like a one marker, but I committed. 38 minutes I've been doing this video. I'm tired, but I got the right answer. I hope you're all doing all right. There'll be another video to follow. I'll try and keep it brief. Please do watch this. I do honestly like it if you click like, because it sort of tells me that these are good. Please don't click dislike. I know, well, whatever. You probably do it to wind me up. Please don't. I hope you're all right. And goodbye.